So this is ECE 341 Random Processes, Part 1, Lecture 6. In the past few lectures, we've been looking at different ways of looking at probabilities. We've done some graphics and some visuals to help us out with that, to things like sequential experiments with tree diagrams as an example. Tree diagrams, coordinate plots are good. They definitely can help you visualize a problem, but they are limited, especially in cases where there's a large number of outcomes. So today we are going to try to remedy that difficulty by looking more formally at counting. So this whole topic is about counting. And really the basic idea here is that for large numbers of outcomes, so for large numbers of outcomes, tree diagrams, right? Tree diagrams and coordinate plots, stuff like that, coordinate plots are just not enough. We really want, or we really need, maybe is a better way to say it, we really need some formalized ways of counting. We do know that when it comes to determining likelihood, a lot of times likelihood could just be something as simple as a ratio of the number of times something occurs out of the total number of times possible. So being good at counting can really lend ourselves some tools in trying to find probabilities. I will start this discussion out by just making a note. So in counting, and maybe I'll do this a little bit different. Let's get this here. I'm just going to say in counting, it is always worthwhile. It is worthwhile to always ask a couple questions. And two that come to mind to me is one of the ones that we might ask is, are we sampling with or without replacement? In other words, if I'm pulling out objects, does my pulling an object out eliminate that from a future selection? Or is it something that if you get a particular object, it naturally replenishes itself? As we work through our examples, we'll certainly see cases for both. But if we start out when looking at a problem as to whether it is a case that has sampling with or without replacement, it will help point us to the right kind of counting techniques. So that's definitely one of the questions we should ask. Another one that's worth asking is whether object order, so the order of objects, whether the ordering of the object or the object order matters or not. There's certainly cases where object order matters, okay? And then there's certainly cases where object order doesn't matter. And generally the counting techniques or the counting strategies for those two different situations are different. So if we start, when we start looking at a particular problem and know we have to go through some sort of counting scheme, if we ask, hey, is this something with or without replacement? And is there a need for maintaining or preserving order or not? It definitely will help you try to identify the right kinds of counting techniques in order to do it. So let's just jump right into it. Let's start looking at some different way of counting things. We'll start out with one of the simplest ones. This one is called the fundamental. So we'll go ahead and look at this one. This is the fundamental principle of counting. So one of the most basic rules. They also call this guy, maybe I should just say also called, it's also called the rule of product. And that will become obvious here in just a second as to why they call it that. So it's also called the rule of product. And the basic idea is something like the following. We have a combined experiment. So a combined experiment is just an experiment with multiple sub-experiments. So a combined experiment. And each of those sub-experiments have a certain number of outcomes. So this combined experiment starts with N1 outcomes for the first sub-experiment, N2 for the second, and it keeps going on out until we get to the last one, NK, right, outcomes. So We have k sub-experiments in our combined experiment, and each one of the sub-experiments has their own number of outcomes. Then, if we have that kind of a situation, we can sit there and say something like the number of outcomes here, the number of outcomes that we could count on this is equal to a product going from 1 to k, the number of sub-experiments of each one of those different numbers. So it's a product of n1 up through nk. I could do that, and maybe I'll do that now on the next line. So that would be something like n1 times n2 times, and we're going to keep going out until we hit times nk. The way you might think about this is that there are n1 ways, right? n1 ways to choose the outcome of the first sub-experiment, right? And then it just keeps going down the list until we get to the very last one. And that one has nk ways, right, to choose the final, which we know is the kth sub-experiment. Okay, this is one of those ones where I think we could sit there and say here, right, order matters. So this particular counting strategy is one that order is known to matter. So order matters in this case. This is a counting strategy that different orderings of the same pieces would be counted differently. So order matters. Let's go ahead and give a very brief example of this. I'll try to do this with each one of the different counting methods. We'll give a short example. Later in another lecture, we'll go into some more in-depth kind of examples, and maybe not just give examples immediately after a particular counting technique. Part of what's going to make counting a little challenging is trying to read some problem statement, trying to read some word description, and then identifying what kind of counting technique is appropriate. So in this first example, we're going to go ahead and just already know, I'm going to pick an example that is appropriate to this fundamental principle of counting, this rule of product. And this first example is going to be something like this. How about we try to find out the number of odd two-digit numbers drawn from the set. Let's do 2, 7, 8, and 9. So there's 4 digits, and I'm going to pull 2 of those digits out, and I'm curious how many odd numbers are in there. I could certainly do this with a tree diagram, and I think a tree diagram can be helpful in trying to visualize this, just because tree diagrams aren't appropriate for every large case, and most of my examples here are not going to be large cases. We'd like to have something that we can verify in a more sensible way. Even though tree diagrams might not be appropriate for every case, they can still help us visualize. Here I want an odd number, and I know that what makes a number odd is its least significant digit. So kind of rather than going from left to right on the number, I'm going to go right to left. I'm going to start with the least significant digit. So my tree here would be to find that least significant digit. So the least significant digit first, and then I'll find the most significant digit. For it to be an odd number, there's only 2 numbers up there that are going to give me an odd number, right? 2 and 8 are even, but 7 and 9 are odd. So if the least significant digit was chosen as 7 or 9, then I know that I would have, in the end, an odd number. And then I need to get the most significant digit. In this case, there's only 2 digits. We said we were going to deal with a 2-digit number. And once I've drawn one thing out, I know there's 3 things left, so there's going to be 3 paths off of here. And I'm not going to worry about too much writing those guys out. It doesn't really matter what the last digit is. That's not going to affect whether or not it was odd or not. If I want to find the number here, right, what is the number, right, of outcomes, right? The number of odd 2-digit numbers drawn from that set of 4 numbers, of which 2 of the digits were odd. The number of outcomes here, in this case, we can get by the rule of product. The rule product says there's 2 ways of choosing that first sub-experiment, the least significant digit, and then there is 3 ways of choosing that most significant digit, and we just product them together, and we can actually see that in the tree diagram as well, and that gives us a 6 number total. So there's going to be 6 2-digit numbers that are odd when drawn from that set 2, 7, 8, and 9. This is one of those cases where you could write out every possible two-digit number that comes from these guys, and you could identify indeed that there's only six odd ones that come out of that. Again, when we think about that rule of product, we did say order matters, and I'll just emphasize that here, right? Order matters when we're talking about something like a two-digit number. If I look at something like 27, right, that's a two-digit number that is odd. If I said order didn't matter, then we would say that would be indistinguishable from something like 72. Clearly, that's not the case in this particular situation, right? The order matters. Numbers need to keep their order in order to have meaning or to remain the number that we wanted it to be. So rule of product, a pretty simple one. It's one for which order matters, and we just multiply the number of outcomes for each sub-experiment. And it's pretty straightforward. As a second method that we might take a look at, let's go ahead and take a look at something called sampling with replacement. Sampling with replacement is another technique, so we're going to go ahead and look at sampling with replacement. You might look at that last one. When I was choosing my numbers out of there, I ended up not replacing the numbers that I'd pulled out, right? And so this one we're going to look at as a you can almost think of it as a special case. So this one is a sampling with replacement. So we're going to have n objects, and we're going to pull something out of that n objects, but we're going to allow whatever we pull out to be replaced. Okay, and I'll give an example that will help demonstrate this in a minute. So it's going to be almost identical. So this is almost identical to the rule of product. Okay, so we're going to have something that's a very similar kind of an idea. What's the basic idea on this? We have n distinguishable objects, and we're going to have some sample size, a sample size of k. You can think of that as the number of sub-experiments. And we are allowing this sampling to occur with replacement. So how many objects or outcomes are on this? So the number of outcomes in this case, the count, we're trying to do some counts here, so that number of outcomes is just our count, is going to be equal to n raised to the k, which is n times, and we're going to do that over times n. There's k n's multiplied together, right? What's the basic logic on this? There's n ways for the first sub-experiment, right? Oh, and then there's also n ways, right? N ways for the second. And the reason it stays n is because we had sampling with replacement. Even though the first experiment pulled something out, right? That thing that got pulled out is replenished, right, for the next sub-experiment. And that goes all the way down to the last one, which also has n ways. As long as we've got k sub-experiments and they all can be drawn from the same original n objects, the total number of outcomes is just n raised to the k. Notice here that these numbers can get pretty big pretty quick, which is why these counting methods are so important for us to be able to get a hold of. You wouldn't want to count the number of outcomes manually if n was 1,000 and k was 3, right? You'd have 1,000 raised to the third. That's a gargantuan number. But if you know the rule of product, or you know this sampling with replacement variant of the rule of product, you can get those number of outcomes very, very quickly and with not too much effort. Again, in this particular case, I'll just emphasize this here again, right here. Order matters, so order does matter. The order of the numbers matters in this case. So we're doing sampling with replacement, but the order in which I'm doing these sub-experiments, sub-experiment 1, it's important that we know what outcome came from that first sub-experiment. The order of these outcomes matters. The order the whatever objects selected in these sub-experiments matters. So let's go ahead and do an example of this and hopefully demonstrate how this particular sub-experiment might work, or this particular form of counting. So I'm going to do an example like this. Let's go ahead and take a look at a case of having 11 soccer players. So if you think about a normal soccer team, it has 11 players, and they just finished their tournament, or whatever you want to call it, and they're going to have an after-game meal. So those 11 soccer players maybe go to the Golden Arches, so they go to McD's, right? So they're going to McD's. The coach there says, hey, you can pick any one of the 6 value menus. So they're allowed to choose, right? Allowed to choose, right? Oops. we want to do this as choose. They are allowed to choose, right, from one of 6, or maybe that's not the best way to say it either. Maybe I should say they're allowed to choose from the value menu, right? Something like that, the value meal menu with 6 options, something like that, 6 options. And what I'm interested in here is what are the number of possible orders, right? How many different ways could McDonald's mess this order up? And so we know we got 11 people waiting in line. They're going to choose just off of 6 items, right? So there's 6 value meals sitting there on the thing, and we want to know how many different possible orders could come out of this. So when I look at something like this, I'm trying to ask myself things like, does order matter? And I would say, yes, order does matter. Maybe I'm going to go ahead and give myself a little bit of a drawing here. I'm going to have player 1 and I'm going to have player 2, right? And they're going to go all the way out until we hit player 11, something along those lines. Each one of these players wants a value menu, right? They want a value meal item on there. Maybe player number 1 chooses value meal number 1, and player number 2 chooses value meal number 3, and all the way down to whatever maybe the last guy picks up a value meal number 1, again, something along those lines. The order here matters because if you mixed up the order, right, if we swap the order of these guys, then player 1 would not get the meal of choice to them, right? So getting some drawings going, thinking a little bit about how you might visualize the problem will help you assess whether or not something like order matters. And in this particular case, the order matters because the players want the meal that they choose. The other thing that we would sit there and say is that, hey, when player 1 chooses meal number 1, right, that doesn't prohibit any other player from getting meal 1. McDonald's has a lot of stock in the back room so that they can make as many meal number 1s as they need to for the customers that are out there. So in this way, player 11 is able to get meal number 1. If we did not have sampling with replacement in this, well, after the 6th player, we'd be in trouble, right? Because there were only 6 value meals, and after the first 6 went through, there'd be nothing left. So this is a case, again, where I think a reasonable interpretation of the problem would suggest that sampling is with replacement. So in this particular case, I have an order matters sampling with replacement, right? And I want to find out the number of outcomes. So what is my N? What is my K in this particular case? If you take a look at this particular one, there are, for all the different value meals, there are 6 different choices, right? So the things that we're choosing out of, the number of options for each sub-experiment is going to be equal to 6. And then the number of sub-experiments, in this case, you think of a sub-experiment as a player, is going to be equal to 11, right? So the number of outcomes in this particular case, number of outcomes, once we figured out what kind of counting to do, the math is generally easy. It's trying to find out what is the appropriate counting technique in order to count the situation we have. And so in this particular case, we know it's going to be n to the k, so we're going to get 6 to the 11th. And if you go ahead and multiply that out, that's approximately 363 million different possible orders. So you have that soccer team come in there. Even if they're restricted to just picking one of 6 value meals, there's 363 million different kind of combinations that could give you unique combinations for those 11 players choosing from that 6-item menu, something along those lines. It makes you kind of impressed that McDonald's can get any of it right. If you're just doing any kind of little error, right, you're going to get something wrong. We've all seen that at drive-through or whatever the case may be. All right. So we've had now the rule of product, and we've now looking at a case of sampling with replacement, which allows us kind of a special case or a variant of the rule of product. The next one I'd like to do is I'd like to look at some counting techniques that have to do with sampling without replacement. So let's go ahead and take a look at sampling without replacement. So we're just laying down some some variety of techniques. What I give here is on these descriptions are the normal ways that we can visualize using these particular counting schemes. I will say sometimes you can use counting in surprising ways. So don't be overly rigid in in thinking about these in exactly one way, but the way in which I generally introduce them provides you some pretty good starting point. What's this idea of sampling without replacement? We're going to start with n distinguishable. So we're going to have n distinguishable objects, and we're going to have a sample size of k. And again, I'm going to put in here, we're going to allow that order matters. So you can think of as having a box, it's got n things in it, and I'm going to pull out k of them, okay? And the order in which I pull them out matters. And as I pull them out, they don't get replaced, right? So once they're out, they're no longer in the box. They can no longer be selected again. So we can think of the number of outcomes here. If I'm interested in counting those number of outcomes, the number of outcomes, right, is not too bad to think about. That number of outcomes you can think of as there's n ways to get the first, right, because there's n objects in that box. So there's n ways to get that first piece. Once I pull one out, there's only n minus one ways to get the second thing, right? And that's going to keep going until I get to an n minus k plus 1. That's my kth choice. So I'm just going to be multiplying these sizes, and the size decreases by 1 for each additional sub-experiment or each additional experiment in this combined experiment. If I wanted to come up with maybe a little bit more convenient way of writing this out, I could write this as an n factorial over an n minus k factorial. That's a little more compact, and we'll talk about that as a strategy for actually computing it out on a calculator. We've got to be a little careful on that, but it's certainly more compact. If I had n equals 1,000 and k equals 500, it would be really awkward to sit there and draw that there, right? We'd have 500 terms sitting in there, and that would be a really long sequence of numbers. If instead I just took 1,000 factorial over 500 factorial, that's easy to at least represent. It might not be easy to compute that way, but it's at least easy to represent. So it gives us a compact representation. I'm also going to say that this whole thing has a specialized notation. So the notation that we do, or you'll see in the book, is you're going to see a parenthetical n and subscripted k. Okay, and so what they call this is that they call this the number of k permutations. So this whole thing is called the number of k permutations. So we draw k objects, right, from a sample of n without replacement, and this tells me the number of kind of permutations, the different ways that we can get that done. Permutations are just different orderings of things. So you'll also see this particular case, which we started out by saying sampling without replacement. You also hear it referred to as k permutations, something along those lines. Okay, so we have a slightly different way now of getting a count. Again, maybe worthwhile putting in just a little note here. So I'm going to point to this, and I'm just going to say we need to be careful in how this is evaluated, Okay, if, right, the n or the n minus k are large, right, then n factorial and n minus k factorial, those guys are exceedingly large and may not be reliably evaluated by calculator or computer, either one. Okay, factorials can be really challenging, especially for large numbers. Just a very quick example of this. Let's think of the following one. Let's think of something like having n equal to 1,000, something like that. And then let's think of k being equal to 1. So I have 1,000 objects. My sub-experiment is only one, so I'm going to draw one of the 1,000 things, and I want to know how many orderings there are. Well, we could say that the number of orderings, quite simply, right, number of orderings here is equal to, maybe I should make this slightly different. Let's make this k equaling 2, just so it's a little bit interesting. Let's do k equaling 2 in this case. The number of orderings would be something like this. I know that I have 1,000 ways of choosing the first one, and then I'm going to have 999 ways to choose the second one, right? So if I do that multiplication together, I'm going to get 999,000 ways that I can carry out this particular experiment. Order matters, right? I'm sampling without replacement from an original box with 1,000 unique items, and there's only two things I'm drawing. If I had instead just gone and said, oh, I recognize this as a sampling without replacement, and I know the number of orderings, right, can be represented as n factorial over n minus k factorial, I could write this out as 1,000 factorial over 1,000 minus 2, right, which would be 998 factorial. And what I'll tell you is that your calculator will overflow. Okay, try it out. It'll overflow on that guy. It's likely going to overflow on that guy, and you're going to get an overflow by an overflow. These are gargantuan numbers. So while we can represent it that way, this is true. The evaluation of it is going to get you into trouble. So even though this might be a compact way of representing it on a piece of paper, thinking about it analytically, it might not be the best way to carry out the calculation itself. You might actually need to expand it out and do it that way. And then there's some cases that are just really hard to go about doing a calculation anyway. Let's do a quick example of this one as well. So let's take a look at an example where I'm going to have a set of numbers. I've got the numbers 1, 2, and 3, something along those lines, okay? And what I would like to know is I would like to know, right, the number of, in this particular case, 3-digit numbers. The number of 3-digit numbers that can be drawn from this set of 3, something along those lines. So what I can recognize here, if you go back to what we're doing, right, we're going to be looking at this as a set that is non-replaceable, so it's going to be sampling without replacement. I've got n distinguishable objects. I've got 3 distinguishable objects, 1, 2, and 3. And my sample size here is also going to be 3, so my k is equal to 3. So I'm going to draw them out. Order is going to matter because the different numbers, that order will give us different numbers. Those unique numbers depend on that order. So I know order matters, sampling without replacement, and I've got my n equaling 3, and I've got my k equaling 3. So if I want to know the number of 3 digits drawn from those 3 numbers, I could get that number as being equal to what? I'm going to have n factorial over n minus k factorial. At least I could write it that way. That's going to be 3 factorial over 3 minus 3 is 0 factorial. Okay, so just as a reminder from your mathematics, 0 factorial is defined as 1. Okay, it's one of those quirky cases. So if you get a 0 factorial, that just evaluates to 1. What's 3 factorial? It's 3 times 2 times 1. And we can see out of this whole thing that there's 6. We should be able to get 6 3-digit numbers out of this. In this particular case, because the sample size is so small, the number of digits is so small, I could probably enumerate these out pretty quick. I could have a 1, 2, 3, right? I could have a 1, 3, 2. Then I could put the 2 in the first place. I could have a 2, 1, 3, and I could have a 2, 3, 1. And I could have the 3 as the first. I could have a 3, 1, 2, and I could have a 3, 2, 1, something like that. No other numbers are possible when taken from those 3, right, without replacement and as a 3-digit number. Let's modify this slightly. Let's think of the number of 2-digit numbers that are possible out of this. In this particular case, we're still drawing from 3, right? But we only need 2 of them. So we're going to only draw 2. We're going to still be drawing without replacement. And if we go through and we find out the number of numbers that we get in that, we end up getting what? We have an n factorial, right, over, and it's again n minus k factorial, same sort of counting scheme. This is going to be 3 factorial over 3 minus 2. That's going to be 1 factorial. 1 factorial is still 1. So I'm going to get 3 times 2 times 1, which is going to be equal to 6. There's still 6 numbers on this. And actually, we can see that up here in our previous counting. If we just ignore that, you thought of that as being the number that was left, right, that we didn't choose in there. All the remaining numbers there are still unique. 1, 2 is different than 1, 3 is different than 2, 1 is different than 2, 3 is different than 3, 1 is different than 3, 2. All of those 2-digit numbers drawn from those 3 numbers are unique, and the counting seems again to have done its job and got us the right number. We might try one more on this and just say, okay, well, let's really push it out here. What's the number of 1-digit numbers? Again, I think we could probably guess this, but the number, if we just do it here, now we have our n still 3, but our k is equal to 1. So I can have an n factorial over an n minus k factorial, right? So that's going to be 3 factorial over 3 minus 1 is going to be 2 factorial. That's going to be 3 times 2 factorial is one way of doing this, over 2 factorial. This sort of trick or this sort of technique here is a good way oftentimes to try to help simplify these ratios of factorials. If you've got a fairly large factorial in the numerator and a fairly large factorial in the denominator, take the bigger one, multiply out all the terms until you get to the lower one, and then just allow yourself to cancel those guys. And so in this particular case, we see quickly that that comes out to 3. And that certainly makes sense. If I've got a 1, 2, or 3, and I've got to just pick one number out of there, I'm going to be able to pick a 1, or I'm going to be able to pick a 2, or I'm going to be able to pick a 3. So 3 different choices available on that one. So that's sampling with replacement, right? Where I've got n objects taken k at a time where order matters, something along those lines. There is a variant of this that I think is worth us also talking about. So let's extend this. So next, let's extend this permutation idea. So we're going to go ahead and extend this idea of a permutation. So the way we're going to do this is that we are going to try to find, or we're going to try to do this, we're going to extend this permutation idea by looking at the ordering, by ordering n objects. Okay, so we're going to be looking at n objects with n1 of what you might call type 1, right? n2 of type 2, all the way out to until we get to something like NR of type R, something along those lines. So one of the things that we're going to need to do in this particular case is we will note, right, that n is equal to n1 plus n2 plus all the way out to plus nr, right? Which you could do as a summation, I equaling 1 to r of ni, something along those lines. So this thing that we are looking at, we're looking at a box of objects, right? So I've got this cardboard box laying on the floor. There's n things in it. Let's say there's 10 things in it. And those 10 things have some level of uniqueness, but not total uniqueness. Maybe out of that 10 objects, 5 are of one kind of thing. Maybe there's 5 shoes in there, and then there's like 2 belts in there, and then there's 3 pair of pants, something along those lines. So we know there's shoes, belts, and pants in this thing. But there's no difference among the shoes, there's no difference among the belts, or there's no difference among the pants. And we're interested in what kind of orderings we can get among all of those objects. And we're going to take out all of them, and we're just going to lay them out. Again, order matters, but I'll say now sort of. So let's go ahead and write that out here. In this case, right, order matters. I'll say order matters. But then I might qualify that and say sort of. Well, what do I mean by that? The order between different types, right? The order between different types matters, but not the order within a particular type. So this is a lot of just language or kind of description of this guy. Once we get the counting out on this, we'll do an example, and I think the example will definitely help illustrate what kind of situations this might be appropriate for. So I'm going to call this the number of orderings. The number of orderings, and we're going to go ahead and try to count the number of orderings that are possible here. So that number of orderings, and we're going to give a special letter to this. I'm going to call it M, and that M oftentimes is referred to as what is called a multinomial. is oftentimes called a multinomial coefficient. So we are actually computing here something called the multinomial coefficient. And what does the number of orderings look like? It's equal to n factorial. If I have n things and I just want to know if they were all unique, the number of orderings, I'd get n for the first, n minus 1 for the second, all the way down until I got the last one, in which case I'd be left with one choice, so n factorial. However, we know that the ordering within groups doesn't matter. And how many objects are of group 1? Well, there's n1, and so they have n1 factorial orderings. And we would multiply by n2 factorial orderings for the next one. And we would keep going to until we got to nr factorial for the last one. So the numerator here is the orderings of n things, right? N things where order matters, right? And these other ones are the ways to order among the ni subgroups, which we said are not going to matter because they're all unique. They're all identical to one another. That's maybe one way of looking at it. So let me go ahead and do an example of this as well. I think this example will help demonstrate kind of the intent of this. I'm going to do this in a little bit strange way. I'm going to make the objects within these subgroups unique just for our own purposes of kind of getting an idea of what it's doing. But then we'll recognize that way I'm writing them uniquely doesn't really matter. So I'm going to look at something from a letter standpoint. So I'm going to have a group of 4 letters, okay? My first letter is an A, my second letter is an A, and then I'm going to have a B, so I'll call that the first B, and then there's a second B. So I've got 2 A's and 2 B's. You could think of this as Scrabble tiles, right? I've got 2 A's and 2 B's that I throw into a little bag and I shake it all up. And then I'm going to draw out all of these tiles, right, in a random order. And I'm going to see what kind of word results. So I'm going to get a 4-letter word drawn from 2 A's and 2 B's, and I want to know how many different 4-letter words there are. It doesn't matter whether the first A was used first or the first A was used second in there, right? Because an A is an A. I've only subscripted them here so that we know that there were 2 unique Scrabble tiles, right, that each had an A printed on it. This particular case has what? It has n equals 4. There's 4 objects available to us. The first group, right, the first group, you could think of that first group is the letter A. And so n1 is equal to 2 because there's 2 A's. Now the second group, right, the second group is a B, right? And it also happens to have its number, so n2 is equal to 2. Some things to check here. We know that n equaling 4 is equal to 2 plus 2, which equals n1 plus n2. So we've satisfied that basic requirement for this multinomial, that if I'm going to be selecting from all these n things, but they're divided into subgroups among these sort of indistinguishable subelements, each within their own group, the numbers here have to all add up to the same overall n, something along those lines. So now I want to know basically how many permutations. So we're really looking for how many permutations are there? How many permutations? How many unique or discernible permutations are there? And what we have to do is we have to normalize for all the suborderings within these letters that you really can't distinguish between them. So the multinomial coefficient is the appropriate one here. We have 4 things, and there's 4 factorial ways of ordering that. If you do that as just a calculation, 4 factorial is 4 times 3 times 2 times 1. And that's going to be 24. So there would be 24 ways. If I had 4 unique letters in there, A, B, C, D, there would be 24 4-letter words that would be possible out of that. But because I've got repeated letters in here, right, there are 2 factorial ways that you can order those 2 A's, right? So think about that. Think about what that 2 factorial is. 2 factorial is just 2 times 1, that's 2. That means there has to be 2 A's. I could have had an A1 and an A2, or I could have an A2 and an A1. I could have selected the first A first, or I could have selected the second A first. But because you can't tell when you look at that Scrabble tile which one was which, we don't want to double count that. We don't want to extra count those guys. So we're going to normalize by that repeated count in here. Same thing for the B's here. That 2 factorial is just reflective of the fact that B1, B2 would not be able to be told from B2, B1 in there, right? It doesn't matter on that. So I'm going to have over this 2 times 2, so that's going to be a 4. So I'm going to have 24 by 4, and that whole thing gives me out a 6. There should be 6 different 4-letter words that can be created from the letters A, and B. Because this is a pretty small set, I think we should be able to find all of them. Let me just go ahead and write them out. There would be an AABB, right? There would be an ABAB. There would be an ABBA, right? There would be a BAAB, and then we'd have something like BABA, and then we would have a BBAA. And that's it. There's going to be no other distinct words that would be possible out of that Scrabble bag that has 2 A's and 2 B's in it. Now notice what's lost here, right? I didn't put in the little subscripts in there because they don't matter, right? Whether I had a term that was A1, B1, B2, A2 versus A2, B1, B2, A1, right? Those guys both look like an ABBA. They both look like that Swedish band ABBA, right? It's not going to be distinguishably different. So while I showed the initial subscripts just to let you know that there were actually 2 tiles, the kind of word that we would recognize on there wouldn't know and wouldn't care, and we wouldn't want to count it twice. So the multinomial, it's really just a variant of permutations, but it normalizes, it undoes, if you will, the number of suborderings within groups that are in that subgroup indistinguishable. And it's really useful for things like maybe this kind of letter, the number of words that come out of a selection of Scrabble tiles would be one example of that. Okay. We're getting close to probably one of the most highly used ones that we would like to be able to work on in this particular case. And this is a kind of a different variation of permutations, but it's a case where in the permutation, we're going to say that the order doesn't matter. So let's look at permutations, what you might think of as permutations, right? Where order doesn't matter. Okay, so we're going to look at this case in a permutation where order itself doesn't matter. What we're going to do is we're going to call this by its frequently called name. This whole thing is called, right? This is called a K combination. So rather than a K permutation where orderings are important, a K combination is going to have it where the ordering doesn't matter in there. So a K combination is the thing we're looking for in here. Okay, and the basic idea is that we're going to have our permutation, right? So we could have something like our NK, that's our K permutation, that tells us the number of ways that we can order, right, a group of K drawn from N objects, right? Their order matters. And if we want to say that this combination is one where we're saying that the order doesn't matter, what are we going to do? We're going to just multiply it by 1 by K factorial. If I've got a group of K things, right? K unique things, a group of K unique things, and I want to say that the ordering doesn't matter in there, I just get rid of the number of ways I can order K things, and that's given through the rule of product as K factorial. So this K combination comes from a K permutation, and then we just get rid of all the orderings within that group of K. So we divide by K factorial. You'll probably recognize this. So this is so frequently seen, they kind of have their own notation for it. So they'll use these big kind of rounded brackets. They'll put the N on the top and the K below. And the way we read this is that this is N choose K. So if you've heard the N choose K kind of notation, right? And you might think of this as being, this is the ways, right? Ways to choose K things from N objects, right? Without replacement, so no replacement going on in here. That goes back to those original questions we talked about. Without replacement, and, right, and where order doesn't matter. So order doesn't matter in our end counting. And there's going to be a lot of possible cases on this. Let's go ahead and take a look at how we might compute that out. I knew how to get the k permutations, right? That was just n factorial over, and I had n minus k factorial, right? And then we're multiplying that by 1 by k factorial, probably the more common way. So they just go ahead and put that n factorial on the numerator. They have the n minus k factorial and the k both sharing the same part in that denominator, something along those lines. Add those two numbers together in the denominator. There's an n minus k, right, plus k. That adds up to that n again. And so this actually could have some connections back to the multinomial if thought about in kind of a weird way. I'm probably not going to choose to do that because I think the n choose k, thinking of this as how do we choose k things from n distinct objects using no replacement, so no replacement as we draw them from there, and where the order doesn't matter. I think this one probably works best for trying to line this particular mathematical technique up to a particular problem statement. So probably the most standard way to introduce these guys is through card type of problems. And so I'll go ahead and do that as well. So as our example, let's consider a standard. So we have a standard here. We're going to go ahead and look at a standard 52 card deck, something like that. So we know in that standard 52 card deck, there are 13 hearts, right? There are 13 spades. We've got 13 clubs going on in there, and we've got 13 diamonds. And then the cards within any one of those suits, the hearts, clubs, spades, and diamonds are the suit, right? The face goes from 1 to 10, and then there's also a jack, queen, king, something along those lines. So within any one of those groups, we've got a 1, 2, going all the way up to 10, and then we've got jack, queen, king, something like that. So every single card in the standard 52 card deck is unique and distinguishable, right? So if I get a 13 of spades, it's different than a 13 of hearts, right? And a 10 of spades is different than an 8 of spades. It doesn't matter what card you pick, each one of them is unique. This is one of those cases now where it's pretty easy. We're going to be looking at this overall example of, well, I don't know where my pen just went. N is equal to 52. I've got 52 objects that I'm going to be working my experiment with. Let's go ahead and think about a game of poker where we're going to do a 5-card draw. So let's think of the number of 5-card poker hands that can be dealt. From a 52 card, right, deck. So if you play a little poker, you know some hands are better than others, right? If I got, for example, 4 aces on that draw, I would be really happy. I'm curious how many different poker hands can just be initially dealt to me. So if you think about cards, usually when you have a dealer, they'll shuffle up the deck and they'll deal you 5 cards. You might get something like the following. You might get a king of hearts, right? A jack of hearts. You might get a 2 of spades. You might get a queen of hearts, and you might get like a 10 of hearts, something along those lines. Now, just because that was the way it was dealt to me doesn't mean that that's probably the way I'm going to keep it in my hand. Almost every card player will sit there and sort their cards so that they can kind of get an idea of what they've got. So most likely, if someone here might do something like this, they might do that king of hearts and see that they've also got a queen of hearts right by it, and a jack of hearts, and a 10 of hearts. This is actually looking really dang good, but then that came that poor old 2 of spades. So we're not quite to that full 5-card straight, something along those lines. But this sorting, this ordering of my hand does help me get a better idea of what's going on in there. And in the end, it's that sorted hand that we look at to find out what kind of hand we have. We don't care that we got a king, jack, queen, 10, in some sort of weird order. What we care about is that there's the king of hearts, queen of hearts, jack of hearts, 10 of hearts, that sequence. So ordering this guy, in whatever ordering scheme you do, is what we do. We resort it, we reorder it from what it was dealt to us in. In other words, the original deal order doesn't matter. So order here doesn't matter to what kind of hand I've got. So this absolutely fits into that idea of a K combination, this N choose K. I've got a 52 card deck. I'm going to be choosing 5 cards, and those 5 cards, the order that they were dealt to me doesn't really matter. I'm going to be sorting them to my preference anyway. So the number of 5 card hands here, at least for ones that matter to us and trying to decide, likelihood of, whatever kind of hand we get, is going to be what? It's going to be 52 choose 5. If I wanted to go ahead and compute that out, that's 52 factorial over 52 minus 5, that's 47 factorial, and 5 factorial. Now again, probably in this case, even though 52 isn't like, hugely tiny. It's possible that a calculator could deal with this, but if I wanted to be just a little bit better in my calculations, I might expand this out a little bit. Remember what we said: if you have a ratio of 2 large factorials, right? Take that bigger one, in this case 52, and then keep multiplying it down until you hit the other one. So 52 times 51 times 50 times 49 times 48 times 47, and leave that 47 as a factorial. Then I'm going to divide by that 47 factorial such that, in this case now, the 47's cancel, and I'm left with a 5 factorial, and that's going to be like a 5, right, times 4 times 3 times 2 times 1, something along those lines. I might be able to do some other stuff, right? So if I took a look at this particular case as well, I know that 6 times 8, right, is 48. So this 6 here could cancel with this, and that would just give me an 8 in there. I know that that 5, right, would easily go here, and that would give me like a 10. And I could take this 4, and I could put it into that, and that would give me a 2, something along those lines. And now I've got something just a little bit easier, right? I could look at this whole thing as being 52 times 51 times 49 times 20, something like that. And that one is going to be a lot safer to compute on basic computing technology than ratios of large large factorials. So just a heads up, you definitely need to watch that. Just plug in something in MATLAB, and just because you express it correctly in MATLAB, you tell MATLAB to do a factorial divided by another factorial, does not mean that it will necessarily evaluate correctly, especially if the size gets large. I think that's enough for today. So we've covered the basic counting methods. Next time, we'll probably look at a bunch of different examples of these. We'll also look at some cases of dealing with some reliability type of problems and a few other related concepts. So that'll come up next time.